In this video, we'll summarize some of the conclusions that we saw from the previous example and discuss how we find eigenvectors once we know that we have an eigenvalue of the matrix. So let's suppose that A is an n by n matrix, and suppose that we want to determine whether or not lambda is an eigenvalue of A. So what we saw in the previous video is that lambda is an eigenvalue of A if and only if the following homogeneous equation has non-trivial solutions. So we look at A minus lambda times I, we multiply that by the vector x, and we look for solutions x to the homogeneous equation. The non-trivial solutions to this are precisely our eigenvectors for lambda, and if there are no non-trivial solutions, then lambda was not an eigenvalue to begin with. So the non-zero vectors x that are in the null space of this matrix, A minus lambda I, are precisely the eigenvectors of A with eigenvalue lambda. Finally, we'll call the null space A minus lambda I of an eigenvalue lambda, we'll call its null space the eigenspace that corresponds to this number lambda. So let's look at an example. I have a 3 by 3 matrix, and I claim in this example that 2 is an eigenvalue, so lambda equal to 2 is an eigenvalue of the matrix, and moreover I claim that the eigenspace is in fact two-dimensional. So what we're going to do is look at the corresponding homogeneous equation and find the corresponding eigenspace. We'll find a basis for it, and then determine the dimension by counting how many vectors are in that basis. To get started, we'll look at the matrix A minus 2i. Remember, when we do this, we're going to take 2 away from all the entries on the diagonal of A. So I'll take 2 away, I'll get 0, 0, and minus 1. And because I has no non-zero entries off the diagonal, we're going to leave all the remaining entries of A alone. We then row reduce this matrix. We'll have a pivot only in the third column, and remember that we'll want to have any rows with zeros move to the bottom. So when I'm done, I will have the following matrix. I have 2 columns without pivots. Those will correspond to free variables. And I have 1 column with a pivot. If I think about the solutions here, I'm saying that x3 must be equal to 0. And I'm saying that x1 and x2 are free. So in matrix or vector form, I'm going to have 2 vectors in R3. I'll have x1 and x2 as free parameters. In both cases, x3 must be 0 according to the first equation in my row reduced matrix. So I'll have 0 and 0, and then we're going to record the value of x1 by putting 1, 0, and we'll record the value of x2 by putting 0, 1. And so really what we're seeing are the vectors e1 and e2, and they span the set of solutions to the homogeneous equation for this matrix A minus 2i. Its null space is spanned by e1 and e2. This is the lambda equal to 2 eigenspace. Of course, those 2 vectors are linearly independent. Therefore, this is a basis for the null space of A minus 2i, the eigenspace, and therefore the dimension of that null space is 2. Let's spend a quick moment just visualizing what this result tells us. Here was our matrix. That determines a transformation from R3 to R3 by taking t of x and multiplying it by A times x. So the domain will be R3, and the codomain will be R3 as well. And what I'm telling you is that anything that is in the xy plane here, where here's the vector e1 and e2, anything in the bottom plane here, the xy plane, anything in their span, is a lambda equal to 2 eigenvalue. So when I apply the transformation from a vector that's sitting in the plane, it will get scaled by a factor of 2 over here. And you should imagine this transformation dilating the xy plane by a factor of 2, stretching everything out about the origin by a factor of 2. What happens for vectors that are not living in the xy plane is not at all clear from our calculations at this point. We're only discussing what's happening in this eigenspace, which is span of e1 and e2.